right, so we want to think about the Coriolis and centrifugal forces, and I'm thinking about a few different ways. First, I want to show how you connect this dq dt equation to the equation with the Coriolis and centrifugal forces. It's not immediately obvious that these are the same thing, and it's because you have to be careful of all the stuff I talked about in the last video. And then I want to think about visualizing the Coriolis force and a couple specific cases of the Coriolis force. The centrifugal force is maybe a little easier to think about. It's something you have regularly experienced. Anytime you whirl something around and you feel it pushing out in the rotating reference frame, there's a centrifugal force outwards. When you go around a corner in the car and you feel yourself pushed to the outside of your car, that's a centrifugal force in the accelerated reference frame of your car. You feel this all the time. The Coriolis force is something you don't feel as often. You may have, if you've ever walked around on like merry-go-rounds or turntables, you may have felt the Coriolis force there. So I'll spend a little more time with that. Now, there is interesting stuff in the centrifugal force, like in the book, where he derives that the direction of gravity and the direction of down is not the same, because the centrifugal force is off at a different angle, and the vector sum is what makes you think of as down. Scary stuff, but I'll leave that for the book. All right, so first of all, let's come back. You've got this equation here, right? Our classic, take a vector q, its derivative evaluated in the inertial frame on the left side. How does that relate to its derivative evaluated in the rotating frame? That's this first term, dq dt sub curly s. That's supposed to be a curly s there. So, great. Then you have this equation, which is equation 9.3, although I'm going to divide it by m. You have r double dot, dots are a little hard to draw with this thing, is equal to f over m, which if I stopped there, hey, that's Newton's second law, inertial frame. But we're in a non-inertial frame, so we have plus 2 r dot cross omega plus, and this is the really neat one, it's the centrifugal force, omega cross r cross omega. Hey, look, all the cross products. Now, you might think I could just take q and make it v, and dq dt would be the acceleration, which is the v we have on the left. Right? In fact, let's just even do this. We could have this acceleration, and I'm going to come back to this and change this equation in a little bit. It's equal to f over m. So I'm taking the equation just above, plus 2 v dot. That's not what I wanted, because that's not supposed to be a dot. Let me erase that here. How do we erase? I think with this. Yep, that wasn't supposed to be a dot. It's now not a dot, and that's good. Okay, plus 2v cross omega plus omega cross r cross omega. Okay, all I've done is just rewritten that previous equation where r dot is now v. And this on the left is a, which is just v dot. But then why don't I take this top equation, subtract omega cross q from both sides? Why don't I just have a is equal to a in the inertial frame, and that's what F equals m is, plus one more term, but instead I have two more terms here. So what the heck is going on here? Well, you got to be careful here. In this equation here, this a is actually the acceleration measured in the primed frame, and this v over here is measured in the primed frame. And that is part of the key difference here. That's what you have to be really careful about this. So this r double dot is evaluated in the rotating frame, so I should call that a prime. This r dot over here is evaluated in the rotating frame, so I should call that v prime over here. So I need to be careful about all of that. Well, okay, so how do you make this all work? So let's clear this off, get a blank slate. Let's just start with, and we'll do it specifically for r here, dr vector by dt in the S0 frame is equal to dr vector divided by dt, not divided by, it's a derivative, whatever, we pretend it's a quotient, in the S frame plus omega cross r, where omega is the angular velocity of the rotating frame relative to the non-rotating frame. And I'm going to just take a derivative of both sides here. d by dt, partial, not partial r, this is a full derivative, dr dt in the S0 frame is equal to d by dt, and I'm just going to do it, I'm going to distribute in the d by dt here, s plus d by dt of omega cross r. Now, there's something I haven't said here that I should have said. This d by dt is in which frame? All of these d by dt's right now with what I'm doing are evaluated in the inertial frame, in the S0 frame. That's important. I need to make sure I do that. So on the left, so d by dt of, so dr dt is already v in the S0 frame. So this is just going to be r double dot in the inertial frame. That's what I have on the left. That's all I've got. And then on the right, well, let's see what I have here. I have a partial derivative of a thing in the S0 frame. I can use the dq dt equation on that. And so that's going to give me the partial derivative of the thing in the S frame, not the partial derivative, the derivative, the time derivative in the S frame. So that's going to be a d squared r dt squared in the S frame. So what I've done is I've taken this term up here. That's a derivative in the S0 frame. I'm going to use that dq dt equation to expand it. So I've got that, and then I have to add the next term, which is going to be an omega cross this thing that we're taking the time derivative of, which is dr dt evaluated in the S frame. Okay, plus, I'm running out of space. Up here, I'm gonna stay in the inertial frame for now. We're going to have a d omega dt cross r plus omega cross dr dt, and I will be clear that this dr dt is measured in the inertial frame. I'm trying to draw 0 on here. There we go. Okay, now we're going to work specifically in the case where omega is constant. All right, so this is a special case because omega doesn't have to be constant, but we're going to work in a case where the rotating reference frame is rotating at a constant rate with respect to the non-rotating frame. So d omega dt is 0, right? So omega is the rotation of the rotating frame relative to the non-rotating frame. If that's constant, that derivative has to be 0. Good. Okay, so I've got that. So let's go ahead, watch, keep an eye on this, and I'm not going to, I don't have multiple boards to use anymore, but you can always scroll back in the video to see what was there before. I'm going to rewrite this again. So again, what we had on the left side was r double dot in the S0 frame. I'm just going to write that as F over M, right? Where this F is just all interaction forces. This doesn't include any Coriolis or centrifugal forces. It's all the all the forces that exist in the inertial frame. Well, we had r double dot in the inertial frame, so that's F over M. That's just what it is. On the right side, that first term inside brackets I had is r double dot measured in the S frame, okay, plus, and then what I had was omega cross dr dt measured in the S frame, so I'm going to call that V in the S frame. My omega is ugly. That's supposed to be an omega there. Sorry. And then plus omega, so the d omega dt term went away. I had a derivative in the inertial frame. I want to get everything, or sorry, I had a derivative in the non-inertial frame at the right here side here. I want to get everything in the inertial frame, so let's use that Q equation yet again. So I'm going to have dr dt. So this was dr dt S0 is dr dt in the S frame plus omega cross r. And now I can just play algebra with this. I got a thing here that I want to get rid of. All right. I can just play algebra with this. This is equal to, well, r double dot in the S frame still. I'm just going to copy that along. Plus, and now I'm going to write this as exactly the same thing, plus omega, I didn't need that parentheses, cross V in the S frame. plus, and now I'm going to factor this omega in. I have an omega cross, hey, what is dr dt in the S frame? That's V in the S frame, plus omega cross R. The parentheses are important here. You remember what I told you last time. The associative principle does not always apply to cross products. If I tried omega cross omega, I'd get 0. But omega cross, quantity omega cross R, is not 0. So those parentheses are pretty important here. Okay, and notice I've got two terms that are the same here. So what I've got is R vector double dot in this inertial frame plus 2 omega cross V in this inertial frame plus omega cross R. That's what I've got. So what I really want to know is, what is this acceleration? So I'm going to move it over to the left side, right? And then move this F over M to the right side, and then all these other things I have to subtract off. So I have over M minus 2 omega cross V, evaluated in the S frame, minus omega cross R. And remember, the R, it doesn't matter if I evaluate it in S or S prime, because R is what it is. Just make sure you're using consistent components when you're doing your cross products. Okay, and this is R double dot in the S frame. So if you look at what we've got here, we have got everything in the S frame now. Well, F is all the quote unquote real forces, all the forces that are not inertial forces, right? So everything from an interaction, your gravity, your electromagnetic forces, your things pushing around, your friction, whatever, all of that. And then omega is the relative rotation of the rotating frame, and then I have V in the S frame, and I have R, right? All that. So if I multiply both sides by M now, and now I'm not going to write the sub S because everything is in the rotating frame. M R double dot is equal to F, all the forces that aren't inertial forces, plus, and now I'm going to reverse the order of the cross product so that I can write it as a plus, right? That's the answer to one of those reading questions. Plus M times, and then I'm going to reverse the order of the outer cross product, so omega cross R cross omega, to flip the sign there as well, right? And this here, oh, I don't like that little bottom line, it'll go away. That expression is the expression for the acceleration, or really the net force on an object in a rotating reference frame. Now, this is the special case where omega vector is constant. So the rotating reference frame is rotating at a constant rate with respect to the inertial frame. F is all the forces from interactions, gravity and electromagnetic, things pushing around, friction, etc. Then you have these two other terms. This term is the Coriolis term. This term is the centrifugal term. Okay, so the videos I've shown you and the pictures in Taylor have omega off at any old angle, so the cross products and things can lead off to things pointing in any old direction. But I think it'll help understand what's going on with these forces if we actually try to do a simple example. So here's the simple example I'm going to do. I want to work, just for now, in the example where omega is entirely in the z direction, right? So I'll draw some axes here. Here's x, here's y, and then z is out of the page here. And what we're looking at, this would be like on one of those little turntables that you see in playgrounds. So you're looking down on a turntable. Here's the center of it, and omega is out of the page. And then let's put a little thing on the edge of the turntable here, like that. Well, okay. And let's just start with the thing at rest in the rotating reference frame. So you know in the non-rotating reference frame, it's not at rest. But if it's at rest in the rotating reference frame, we can figure out mr double dot. Well, r double dot's going to have to be 0 if it's at rest and it stays at rest, right? Is equal to F, all the forces, the actual interaction forces that are on it, plus 2m v cross omega, but we have asserted that in the rotating reference frame, which is what this v is 0, plus m omega cross r cross omega. And notice here, r, let's go ahead and call that distance r vector is just rx hat. And what's nice about that is that you can figure out omega cross r. You can either use the right-hand rule, or you can just take omega is in the z hat direction. So you'll have omega z hat cross r x hat. Z hat cross x hat is y hat, so that becomes omega r y hat, that cross product, which you then want to cross with omega z hat. And y hat cross z hat is x hat. So we have 0 is equal to f, and the second term went away, and so what I'm left with is plus omega squared. Oh, there's also the m out front here. Ooh, go away. M omega squared r y hat cross z hat is x hat. Or space management problems. So let's set some space off here, and I'm going to go up to here. I get f is equal to minus, try again, f is equal to minus m omega squared r x hat. What is that f? It's got to be something, right? For this object to be at rest and to stay at rest, I must exert a force on it. So maybe I've glued it to the turntable, or maybe there's a static friction force holding it in place or something. But we know there's got to be a force on it, so there has to be some sort of interaction supplying that force. If you look down here at this equation at the bottom, basically what that says is there needs to be a force to offset the centrifugal force. Centrifugal force, but I say centrifugal and pronounce it with the emphasis on the wrong syllable, so you can tell I'm not saying centripetal force in the sense of centrifugal force. All right, so remember this. I'm going to come back to it in a moment. But for now, let's go back into the inertial frame. In the inertial frame, I have this turntable or whatever, and here's an object. In the inertial frame, it's moving at some speed v, and this is, here's omega, here's r. We know in this special case that v in magnitude is equal to r omega. And v vector is in the y hat direction. Just look at it, right? Again, we have x that way, y that way, and z out of the page. All right, so that's v is omega n. And you know from physics 151, to stay in a circle, there has to be a centripetal force to keep it, right? We're working in the inertial frame here. So there has to be some sort of centripetal force. Is it static friction? Is there a string tied to it? I don't know. But there has to be some sort of centripetal force whose magnitude is mv squared over r. And in this case, if you look at it, it has to be in the minus x hat direction at this instant because it has to be towards the center. Now, of course, that's not true later when the thing is rotated and when the particle is up here, then the force will have to be in that direction. But right now, we're just talking when the particle is right there, just instantaneously. Well, okay, but of course, we know what v in magnitude is, so that's going to be minus m r squared omega squared over r x hat, or minus m r squared omega squared, m, oh goodness. So now I have to erase again, which is a little cumbersome here, but right, the r squared over the r canceled down to just an r. So mr omega minus mr omega squared x hat, that is the centripetal force that we need. And notice I got exactly the same thing that I did analyzing it and the rotating reference frame. The difference is here, you say, oh, it's moving in a circle, so I have to have some force to hold it in a circle. That's what we said. In the rotating reference frame, we said we have a centrifugal force. We have to have something to offset the centrifugal force to hold it at rest, right? So that's you get the same sort of interaction force. This F has to be supplied by some interaction. A string, static friction, glue. You holding on to it, but that's just a string. Tendons are strings. Well, great, okay. So now let's talk about the Coriolis force. We're going to set up our same axes here. So that's X, that's Y, that's Z. I am still working in the case where omega is in the Z direction. And I'm going to draw a picture, and I'm going to draw this picture in the rotating frame. All right, so there's the center. Omega is in the Z direction. You have a particle here So r for the particle is from there to there. And at this instant, the particle has velocity v that way. So now the particle is no longer at rest. Right? So just to make sure we know what's going on, omega is omega z hat, r vector is r in the x hat direction. And I have set up v vector is v in the minus x hat direction. That's just what they are. Okay. Well, you know that there's going to be a centrifugal force on this. F centrifugal force is equal to m omega cross r cross omega, and that's exactly what we did last time. So I'm not going to belabor it, but that's going to be m omega squared r in the x hat direction. But the Coriolis force, now there is a Coriolis force. So the Coriolis force, that was a vector, Coriolis force is equal to 2mv cross omega. So that's equal to 2m minus v x hat cross omega z hat is equal to minus 2mv omega x hat cross z hat. X hat cross z hat is minus y hat, so this is going to be 2mv omega y hat. Right? The Coriolis force points in the y hat direction. So what that means is that if you follow this particle's trajectory, right, it starts here, it's going in, it should curve in that direction because there's a force in the y hat direction. It should curve up like that in the rotating reference frame, which will look really perverse. All right, so here we are. We're looking at this big round table. It's rotating, but we're in the rotating frame of reference, so you don't see that, right? It's just like on the Earth. We don't see the Earth spinning. We're just on it. Every so often you vomit, but that's not because of the rotation. That's because you're sick. So don't do that. So here it is. And then there's a particle, and currently we are just holding the particle in place. We have to hold it in place, right? Because there's a centrifugal force, so we have to offset it somehow. So we're holding it in place. And what I'm going to do is give this particle a kick down and to the left. Now, this is a little different from the example I just did where I kicked it just to the left. That's what I did when I was drawing things out. This time I'm going to kick it down into the left. So what you're going to see at some point here, pretty soon, is that the particle is going to start moving down into the left, but it won't keep moving down into the left. So I give it this kick down into the left and watch it. Right, notice, it did curve in the plus y direction. It's a little different from the example I just did, written out, because it was straight to the left. But yes, we would have gotten the same thing. There would have been a force that would have had a component in the plus y direction. And that's what you got. And so, right, if we watch this again, as this particle goes, we kick it down into the left. But not only is there a centrifugal force, there's also a Coriolis force that depends on the velocity that changes over the course of the particle's movement. And as a result of it, I kicked it at exactly the right rate that it ended up right back where it started. And that just looks wrong. Right? The only way you're going to get weird curving like that is with Coriolis forces. Well, so what was really going on here? Well, what was really going on here is that was in the rotating reference frame. The way I made this movie was I set it up in Blender, right? And I just animated little stuff. And I had a camera, and the camera was rotating at exactly the same rate as the table, so you didn't see the table moving. Well, here's a camera that's not rotating. This is an inertial camera, and you can see the table rotating, and you watch the particle fixed going to it. And what's going to happen is I'm going to kick the particle. I'm going to stop it so it's v equals 0, and then kick it to the left so it has, boom, there it goes, a velocity in the negative x direction. And in the inertial frame, assuming there's no friction here between the particle and the table, in the inertial frame, it just moves straight across, right? Watch this again. I stop the particle, and then instantaneously thereafter kick it to the left. So the particle's coming up, it's coming around here, and then, boom, I kick it to the left, and it moves in a straight line because there's no forces on it. In the inertial reference frame, there's no forces on it. It moves in a straight line. But notice that the pattern was still moving. And the relative motion of the pattern and the ball is exactly the same as what we saw in the other reference frame. So let's watch this whole thing in both reference frames at the same time. On the left, we've got the inertial frame. On the right, we've got the rotating frame. That's pretty obvious right now. And then what's going to happen is I'm going to, in the inertial frame, stop it and kick it to the left. And the rotating frame, that's the same as kicking it down and to the left, right? Because stopping it is effectively kicking it down. And you'll see that the motion, and if you look at where the ball is relative to the wood pattern, you'll see that it all kind of works out there. So this is, and I'm going to post a link to the website of this classic old from like the early 1960s or even the 1950s black and white physics movie all about reference frames. I'm pretty sure I actually showed it in this class earlier. I know I've shown it to a few of you before because I just love this movie, partly because it's so late 1950s, early 1960s, or whenever it was, physics movie with these guys in suits. But it's really a neat movie talking about moving between reference frames, both in terms of orientation as well as linearly moving frames and rotating frames, and it has exactly that same little demo I just did. Well, all right, so one more thing. The Coriolis force is just an artifact of the fact that you're in a rotating reference frame. Now, in that reference frame, you will accelerate relative to the reference frame. So the Coriolis force is a real force in that sense. It has a real effect. It causes things to move. But it's really, and that's what the two videos I just showed you, it's really just, it's the effect of the fact that your reference frame is accelerating. Well, here's another way I want to think about the Coriolis force. So here's a big circle. Imagine this is a rotating disk. Then I've got a line here. And as this thing rotates around, so I'll draw it, sometime later it'll be there, right? The thing will have moved through some angle theta. Now you're having horror flashbacks to the test. If I look at each point along this, right, that point has to be moving at that v. This point halfway along has to be moving at about half the v. This point is not moving, right? That point's moving at that v. This point's moving. Each point along here is moving at exactly the right v so that you will have, well, you could do this with, right, v is going to be omega. Oops. Oh, here we go again. Now I do my little erase. You have to make the noise when you erase, otherwise it doesn't work. Okay. I have v is equal to omega. I need to learn how to write. Beepo, beepo, beepo. Bigger. Beepo, 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 beepo. And I don't know what I just did. Do that. V is equal to omega cross r, which in this case omega is in the z direction, r is down. You get it, so they're perpendicular to each other. I would get v equals omega r. Oh, look at that. We already knew that. So this r here is twice as big as this r, so the v is twice as big. So all the v's are just depending on how far they are. Well, now consider a particle that's right here. And let's just move the particle towards the center. We're going to move the particle from there to there. This particle is now moving at a speed that is faster than what the particles that are just on the disk are moving. So that means the particle, because it's moving at a faster speed in the rotating reference frame, it's going to look like it goes that way because it's moving too fast now it's moving too fast for the particles that are right there. And so now, really wish me luck here. I'm going to try and draw in 3D for the surface of the Earth here. Right. So if you imagine, here's the surface of the Earth, and you have something that's at the equator here, and suppose you have your low pressure system, whatever. For some reason, stuff is pulled up in that direction. If it's pulled up in that direction, well, it's still moving at this same speed v now. However, things at this point are only moving at some slower speed, like that. So as the Earth goes around, one way of looking at it is this particle here, when it moves up here, now gets ahead of the things that are moving. By the way, why is it moving at a slower speed? Because it's closer to the axis of the Earth, right? Right. So that radius is less than that radius because the Earth curves in as you go around. So if you look at it in the inertial frame, this guy that's moved from here up to here now runs ahead of the other things that happen to be right there. So this is why you get the thing going like that, you'll get the that'll give you sort of the direction of the cyclone's low pressure system. Whatever. All right. So the Coriolis force, it's an interaction between the velocity in a rotating reference frame and the fact that the frame is rotating. It will cause you to have an acceleration relative to the rotating reference frame, which, as we saw with the turntable example, in an inertial frame, that thing that was moving had no acceleration at all. Now, you might have an acceleration. There might be real forces, right? But in an inertial frame, you can have no acceleration. But if the frame is accelerating, then, well, you have an acceleration relative to that frame. And if you want to analyze things in that rotating reference frame, you have to add these inertial forces, which in the special case of a frame that's rotating at a constant rate, you can use the centrifugal and Coriolis forces using this expression that we have in Taylor. All right, that's all for now. Now, based on what you guys say in the reading questions, I might on Monday, I'm recording this Sunday, even though I'm posting this Monday, I might on Monday record one more video with answers to questions. All right, that's all for now.